All right, video 7, calculating confidence intervals for one mean. So really, most of the chapter we've been doing proportion level problems and calculating a confidence interval for a proportion. But now we're going to start working on some mean level problems here. So in the last video, we talked about this new idea that we're no longer going to have a z-score as our critical value. We're going to have a t-score based on the t distribution. And I have already given you, if you spoke up and you were there that day in class, that if you have a TI-83 plus, that you need the inverse T program to be able to figure out your critical value. So hopefully you have that so that you may calculate what we are going to work on today. In your, well, no, not there yet. Our statistic is going to be our x bar. It used to be p hat, but now we're switching gears. It's an x bar now. Our critical value is going to be our t-score, and the standard error of the statistic. That is nothing more than from last chapter, our sigma sub x bar, which typically was sigma divided by the square root of n, but we don't know what the population mean is, so we said we may substitute out sigma for the sample standard deviation s. Okay, so in your formula sheet, again, this is what it looks like. This is the same screen I showed you from the proportions. This is what it says for confidence intervals, and it's pretty much exactly what I just showed you, except I called it standard error of the statistic. They call it the standard deviation of the statistic. But since we don't know the population standard deviation, then we call it the standard error of the statistic. So statistic really just means one of two things, either sample mean or sample proportion. We're now going to be dealing more with sample means, so we'll be using x bars. The critical value is going to be that t-score. It's really going to be the only thing that doesn't reveal itself on the formula sheet. And the standard deviation of the statistic, well, they're saying that's this column right here. And since we're dealing with means, we're going to be dealing with this. And again, since we don't know what sigma is, we get to replace it with s instead. Okay? So the formula sheet doesn't exactly spell out what the formula is, but you can plug in those values into the words up here. Now, the conditions, we talked about them in the last video. They're all the same pretty much for proportions, especially the first two here. So you still have to check, is there a random sample? We mentioned before that if the sample was taken in such a way that would produce a large amount of bias, for example, with a volunteer sample, for instance, you probably just don't want to do the whole thing at all. You know, mention that the sampling technique, the sampling method, it will produce a high level of bias. So whatever confidence interval you come up with is pretty much going to be useless. If they don't mention at all what kind of sampling method that they took in place, then we're going to go ahead and do it, but we will say sample is not known to be random, so proceed with caution. You still have to check the independence condition. Is the population at least 10 times the sample size? If that does check out, you may then calculate your standard deviation, which is our sigma sub x bar, which we just mentioned earlier. It's going to be our s divided by square root of n. You may calculate that now. If this condition is not met, then, as we mentioned earlier, there is something to fix that, but we don't really work on that in this class, so we will just say standard error cannot be calculated. And the approximately normal condition. This is where you can use the central limit theorem, but we can't really say normal at all. The main reason why we're going to use a t-distribution is because we don't know the population standard deviation. And the population standard deviation does go kind of hand in hand with a normal distribution. So what I have written here is we can use the central limit theorem, but we can't really call it approximately normal. We could call it approximately t. Okay, we're still going to be able to use the t-distribution. If our sample size is less than 30, t-procedures can be used except in the presence of outliers or some strong skewness. Now, here's the thing, we're going to have some data. So we will have to plot our data Either with a stem plot or a box plot are good ways of checking that out, and we will have to do that. You absolutely have to do those, one of these two things, to ensure that there isn't any outliers. And a box plot, if you remember how to do that in your calculator, can show you if there are outliers present. So maybe a box plot might be the better way to go. So I'll show you both, a stem plot and a box plot, to show you the advantages, disadvantages, maybe the other. If the data checks out, if your plot checks out here, then you can say, based on the data shown, we may assume a t-distribution with blank degrees of freedom. And remember your degrees of freedom from last video, or whatever your sample size was, -1. And if the data are clearly skews, or if you see outliers from when you do this up here, then you will just say you cannot use t-procedures. You may not assume a t-distribution. So stop, do not proceed, don't do the problem. All right, so the example we're going to look at here, put this up here, says a company manufactures portable music devices called M boxes. This sounds kind of familiar if you know what I mean. For the listening pleasure of on-the-go teens like you guys. The M-Box uses batteries that are advertised to provide, on average, 25 hours of continuous use. The students in Mr. Jones's statistics class, looking for any excuse to listen to music while doing their homework, who would do that, silly kids, decide to use their statistics to test this advertising claim. To do this, new batteries are installed in 8 randomly selected M-Boxes, and they are used only in Mr. Jones's class until the batteries run down. Here are the results for the lifetimes of the batteries in hours. So here's our data here. It says construct and interpret a 95% confidence interval for the mean number of hours, mu, that the batteries can be expected to last. Okay, so we're going to create a confidence interval that hopefully captures the true mean number of hours, mu, that the batteries can be expected to last. So first, our conditions. So condition number 1. Do we have a random sample? And up here it does say that they were randomly selected. So I'll just say random question mark says so. Check. Condition 2. Independent? Well, we need to check. Is the population at least 10 times our sample size? Well, the population would be all what? All batteries? All hours? You got to think about, what did we sample? Well, we sampled 8 M boxes. So really, we're talking about all M boxes. Is that greater than or equal to, we would plug 8 into N, and can we assume that there are probably more than 80 M boxes? Yes. So we will assume true. Therefore, we may later calculate the standard error, or the standard deviation of our statistic. And last but not least, the third one. Can we assume that we have a normal or approximately normal distribution? Or really, it's not even normal anymore. It's, can we use t-procedures? So what we need to check here, we have a small sample size, so central limit theorem is not really going to kick in. We do have a fairly small sample size of only 8, so we need to plot our data here. Now, I've already got these two things plotted, and I did this on my calculator, okay? All I did was I put all my data up here into list 1, and then I went to second, and then my y equals button, which is for my stat plot. And from there, I found the box plot, the one that has the picture that shows outliers on it, shows you the little dots here. Those meant that they were outliers. So I selected that one. I said use list 1. I graphed it. I did zoom 9 for zoom stat to make it fill up the screen. And this was the picture I got, and I took a picture of it and stuck it in here. Now, based on my box plot, there were no outliers. There were no values kind of hanging out over here or up there. Okay. Now, if I look at this, can I tell if there's any strong skewness, like extreme skewness going on here? No, not really. Or if I want to do a stem plot real quick. So I made my stem plot, I included my key, and if I look at this, I don't really see any extreme skewness, if you will. It's maybe slightly skewed, but it's pretty fairly symmetric, okay? So we will say, based on the box plot, or we could say based on the stem plot, the data can be assumed to follow T procedures. Check. Okay, now we can do all the work. Yay! Now we get to do our calculations. Okay, so here is our formula we're going to use. So x bar, I need to figure out the mean of all my numbers. Well, here's what you could do. If you made the box plot from list 1, what you could then do to figure out what a lot of these numbers are going to be, really 3 out of those 4, and one of them's already known, you could go to your stat button and then go over to calc and then do one variable statistics and select list 1. And it's going to give you the sample mean, which is 22. Plus or minus, we'll come back to the t-score. The S, the sample standard deviation. In your calculator, it's labeled as S sub x. And in your calculator, you should get, if I do 4 sig figs here, 4.071, and then divided by the square root of my sample size, and I had 8 M boxes. So the only thing we're missing here is our t-score. So let's talk about what that t-score was and how we calculated it. We said earlier on the last slide that we wanted to do a 95% confidence interval. So if I want to consider the middle 95%, this is what I want to try to capture here with my confidence intervals, this middle 95%, we needed to talk about, well, how much room was in a tail, one tail. Well, both tails have 5%, so one tail has 2.5%, so 0.025. And we said we're going to have to use inverse t, which was right below inverse norm, which is right below normal CDF. So if you have the newer version of the calculator operating software, it will ask you specifically for the area, and there you want to put 0.025. If it doesn't, then you just, if it gave you this in your calculator screen, then you type in 0.025. And then if you have your calculator updated, it's going to ask you for the degrees of freedom. If not, you have to know what to put in here. Remember, the degrees of freedom is n minus 1, so degrees of freedom will be 7 because our n was 8. So 7 degrees of freedom. You punch that in your calculator, and if I do, again, 4 sig figs, it does give me a negative t-score, but we said kind of forget about the negative, just write it as positive, because we're really going to be adding and subtracting a positive number or a negative number, and we're going to get the same result. So 2.365. Okay, so now, really, I've got 22 plus or minus, and my margin of error, if I calculate all this here, is 3.404 if I do 4 sig figs. So now I'm going to subtract this from 22 and add this to 22. And typically you do want to put the smaller number first, which you should get, let's see, 22 minus 3.404, I get 18.596, and if I did 4 sig figs would basically be 18.60, but I'm not going to put the 0. And then if I add that on, I'm going to get to 4 sig figs, we'll just say 25.4 instead of 25.4 over 4. So instead of putting that extra 0 there, we'll call it a day. So here, this is my 95% confidence interval. So now I'm done with my calculations. Now I come down to my conclusion, which I already kind of have pre-made out here. So I am 95% confident that the mean, and what were we trying to estimate here? The mean number of hours of battery life for all, what was our population? Our population was our M boxes, is between 18.6 and 25.4. And if we want to put some units in here, we can, because it's no longer just percentages or proportions, hours. Okay? So what we might say here, if we jump back, it said the company claims that we can get 25 hours. So this kind of gives you a clue as to what we're going to do next chapter. Next chapter, we might be given a claim about our population, and we're going to test whether that number is statistically possible, statistically feasible. So is 25 in our confidence interval? It is inside of it. It barely squeaks in here towards the upper range, but it is in there. So we would feel confident that yes, the company is probably telling the truth, that it could be 25 because it is inside of our confidence interval. And that is all for how to calculate a confidence interval for one mean using T procedures.